In this video, we are going to learn the departure functions, and the departure refers to the departure from the ideal behavior. Previously, we have seen the departure from the ideal gas behavior. We have removed the assumptions of the ideal gas law. We have accounted for the volume of the molecules, volume occupied by the molecules themselves, and we have accounted for the interaction between attractive and repulsive forces between the molecules. Knowing this and knowing the general behavior of the energy balance and the entropy balance, we derived the most general form of the internal energy change and enthalpy change functions. We have used the Maxwell relationships to guide us from an entropy-defined thermodynamic landscape to an PVT-defined thermodynamic landscape. Now we have our equations of internal energy change and enthalpy change in terms of a heat capacity and in terms of PVT relationships. Now we are going to address the problem of how we are going to integrate those functions. Now here we have an example of a piston and cylinder assembly undergoing a polytropic process. Polytropic. We really don't know the path, but we are not so much concerned about the path because for this polytropic process, we are defined the initial and final states that the system is going to run from T1V1 state to a T2V2 state, and we are asked to find out what is the shaft work. Now, when we look at this system, the closed system analysis revealed that du over dt is equal to shaft work minus p dv over dt. And let's just leave a constraint that we don't allow any heat exchange. So we have an insulation clad so that we don't worry about this. And we can change temperature by expansion contraction also, right? So this is our final form of our energy balance equation. We really don't know whether our process has any constant temperature steps, any constant pressure steps. All we know is that it's a polytropic process going from T1V1 to T2V2. Now the shaft work is going to come to be equal to, and it's all complexities, and of course we have now a van der Waals fluid, right? This is our van der Waals equation of state. That the shaft work is equal to du over dt plus p dv over dt. All right. So this is what we are looking for. We are going to take the integrals. Let's just do the algebra. Shaft work is equal to integral shaft work over time du plus integral p dv. Now let's substitute du from the most general expression. And I will just combine everything in the same integral for the sake of clarity. This is going to be cv dt plus t del p over del t at constant v minus p dv plus p dv. let me put everything in fancy parentheses to indicate that our integral covers everything. Now when we look at this expression, we see that this PdV term and this PdV term are identical with the difference between the sign in front of them, and they cancel one another. As a result, my integral, or my shaft work, is going to be equal to integral CV dt plus integral, now I'm going to separate the integral, you will understand why in a moment, T del P over del T at constant V times dV. So this is going to be the expression that will allow me to estimate the shaft work. Let's see. And this is the real fluid CB. This is something that is not accessible to us. Not always. But the ideal gas heat capacity is accessible to us. That we have learned for a monoatomic ideal gas, heat capacity is equal to 3 over 2R. For solids that follow Dulong-Petit law, that C heat capacity is 3R, and for the gases, for diatomic gases, the heat capacities are going to have 1 more R for each bond. So if we know our molecule, if we know the molecular structure, under the ideal gas conditions, we know how the molecule will behave under the conditions of heat exchange, and this is going to be through the ideal gas heat capacity, C sub V, but we don't know the real fluid heat capacity. What we are going to do in order to overcome this barrier, we are going to devise a path. See, here we are estimating the internal energy. Internal energy is a state function. Let me put the underscores to be on the safe side. All right, so that we will have the work per unit mole or per unit kilogram of the material. We're going to take a path, and we're going to take a path which will go through an ideal gas state so that we are able to use the ideal gas heat capacities. Now that's going to be something like this. Now we are at state T1, V1, and our system is going to end up at T2, V2. We are not informed about the path, but since we are calculating state functions, we don't care. We know the initial and final states, but we don't have the heat capacities. Now what are we going to do? We are going to take this system from where it is to an ideal gas state. What is an ideal gas state? Ideal gas state is where temperatures are high, pressures are low, and volumes are very, 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 very high. All right? So between the real fluid and ideal gas state, we have those differences, that the pressures are low and the volumes are very, 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 very high. So I'm going to create a state where volume approaches to infinity, all right? And that is going to give me the ideal gas behavior. So what I will do, I will devise a path which is going to take me from my T1 at constant temperature to the ideal gas state, right? So this indicates that I have cut down my path because this is going to infinity. And here I'm at V infinity and T1 at this constant temperature. Here I'm going to carry out my temperature integral. I will go from T1 to T2. All right, here is the state is V is at infinity and temperature is at T2. I took my temperature integral. Then I will bring my gas from the ideal gas state to my real fluid volume temperature pair state. So I have 3 steps for evaluating the property, the change of the state. I have 3 steps. Isothermal expansion to an ideal gas state. Isochoric constant volume heating. Constant temperature cooling to my second state. Now let's come back and see where this is going to reflect itself in this equation. This is going to be, first I'm going to keep my temperature constant, therefore I don't have to deal with this integral. I'm going to take my system from V1 to infinity, that I have a function T del P over del T at constant V. And I have to evaluate this function at T is equal to T1, because that's where I kept my temperature constant, times dV. Now I'm here. After taking this integral, I'm here. Now I'm going to have the freedom of using, have the choice of using ideal gas heat capacity CV star. If I know my molecule, I know the first approximation heat capacity from T1 to T2 dt. Now I have to bring the gas back from the infinity to the real fluid. And here I will evaluate this function at a constant temperature, T2 times dV. Now, this is the ideal gas behavior. And this is the departure function. For this particular problem, why for this particular problem? Because our PDV terms cancelled the way that we constructed this problem. All right? Now, let's leave this problem at this level. I'm not going to go through the integrations. What I will do, I'm hoping that with this example, it was clear that the concept of departure function is clear. Now I'm going to do the general derivation of the departure functions for the internal energy and for the enthalpy. So for the internal energy, the path is here, that we are going to go from the initial state to an infinite volume state where we will carry out the temperature integration as an ideal gas, and we will bring the system back to our original real fluid state. And I'm not going to make any constraints. I'm not going to make any problem statements. The example is over at this level. I'm going to do the derivation for the general internal energy change for a real fluid case. And then I will take that example and I will use the van der Waals equation of state to find the departure functions. Then I will discuss few other real fluid equations of state. Now, du, as we derived, is Cv dt plus T del P over del T at constant V minus P times dV. So U2 at T2 V2 minus U1 at T1 V1 is equal to integral T del P over del T at constant V minus P dV integrated between V1 and infinity to bring the fluid to an ideal gas state. Between T1 and T2, Cv star dt, now that we carried out the temperature integral, plus integral between infinity and V2 T del P over del T at constant V minus P times dV. This segment is evaluated at T is equal to T1. This segment is evaluated at T is equal to T2. And these terms are our departure functions. That we are now able to evaluate the real fluid behavior using information available to us as ideal gas heat capacities. The enthalpy integral is going to be a little bit tricky. I will need a clean board. After I clean the board, I will discuss the enthalpy integral. Now we are going to discuss how we are going to evaluate the enthalpy integral. Enthalpy integral is going to be a little bit tricky because the real fluid behavior is explicit in terms of volume and extracting pressure. To evaluate this integral is going to be a little bit time consuming. We are going to just do the same thing as we have been doing when deriving the Maxwell relationships. We are going to do a change of variable to make the mathematics manageable. So let's start from dH, which is Cp dt plus V minus T del V over del T at constant P times dP. Of course, they all have underscores, that they're per mole. They are intensive. Now, as I said, this extracting volume from a cubic equation of state is not trivial to substitute here to get the pressure integral. So instead, we are going to express dP as a function of P as a function of V and T, and dP as a function of del P over del T constant V times dt plus del P over del T del P over del V at constant T dV. So instead of this, I'm going to have this, so that I'm going to have two terms in the dt and a dv integral. Let's do that. So when I substitute this over here, I have del P over del T at constant V multiplied by this whole group, V minus T del V over del T at constant P times dt Then I have another term for the V integral. Plus V minus T del V over del T at constant P times dt. Well, we have to introduce our pressure variable here. Del P over del V at constant T times dV. Now we are going to evaluate this function over a path. This path was the path to evaluate internal energy change. Internal energy was derived as a function of temperature and volume. Now this new path that we are going to devise is going to be the path for enthalpy evaluation. So let me use a different color to devise a new path for my enthalpy change. Now my enthalpy in this form was a function of temperature and pressure. So my path is going to start from T1, P1, and it will end up at T2, P2. All right? But what will happen is, of course, now let me change the coordinates a little bit. I have to start from way up. It will be from T1, P1, and it will end up at T2, P2. You will understand why I have made this change. All right, now again, we are going to bring this real fluid from where it is to an ideal gas state. And the ideal gas state is where pressure is 0. Pressure is very low. And in order not to have an arbitrary number, we will just like having the volume to be infinity, we will have here pressure to be equal to 0. So we are going to have a pressure to be equal to 0, T1, isothermal expansion all right, wherever the pressure was, to this zero pressure domain, we are going to have an isothermal integral at zero pressure, where our fluid is going to behave like an ideal gas. And then we are going to carry out the integral along the pressure dimension to the final state. Now let's see how our equation is going to behave. H between T2 P2 minus H H1 T1 P1 is equal to, first I have to take my system from the real fluid domain to the ideal gas domain at constant temperature. When the temperature is constant, all those terms disappear. So I'm going to take the system with a V integral, V corresponding to P1, to V corresponding to P is equal to 0, and when pressure is equal to 0, volume has to be infinity. Then I have this. Expression times dV, and this is of course evaluated at T1 plus, now I'm at the ideal gas state. Between T1 and T2, Cp star dt. Then I will come back from this ideal gas state to my real fluid state, from V is equal to infinity to V evaluated at P2, the same departure function. V minus T del V over del T at constant P times del P over del V at constant T evaluated at T2 times dV. All right, so real departure function is this for the enthalpy. If we can evaluate the pressure derivatives explicitly, or if we can extract volumes explicitly from an equation of state, not necessarily van der Waals. But when we make the coordinate transformation, what we have is this. Again, we can do this integral on a volume domain while our path is a pressure domain. Now let us look at how we can obtain the real fluid heat capacities. That sometimes we need real fluid heat capacities. Let's see how the real fluid heat capacity is going to behave given the enthalpy information. Now we're going to just take a step back, and we're going to remember that del H over del T at constant P is equal to C sub P. All right. Then we are going to take the second derivative of this with respect to the other variable. What is this other variable? We're going to differentiate this whole thing with respect to P. Del over del P. Now here we are going to have del over del P times del H over del T at constant P. On the other side, we are going to, of course, this is at constant T. On the other side, we have del Cp, this is the real fluid heat capacity, over del P at constant T. I differentiated both sides of this equation with respect to P. Now remember, when we were deriving the Maxwell relationships, we said that energy is a conserved quantity, and if we have conserved quantities, that it is possible to change the order of differentiation, or if we have an exact differential, which is the other way of reflecting the same concept, that we can change the order of differentiation and the outcome doesn't change. So let's do that here. Del over del T times del H over del P at constant T at constant P is equal to del Cp over del P at constant T. And this term is this group, all right? This term is this group. So I'm going to substitute V minus T del V over del T at constant P all right, differentiated with respect to del over del T. This is going to be del Cp over del P at constant T. Now I have one way of evaluating heat capacity then. What I'm going to do is I will multiply both sides of this equation with dP, all right? Then I'm going to have del Cp on one side. On the other side, I have del over del T V minus T del V over del T at constant P times dP integral. We have differentiated this at constant pressure, by the way, let's not forget. And this is going to be from the ideal gas heat capacity to the real fluid heat capacity, where we are going to integrate this from a zero pressure to the desired pressure. So if you know the ideal gas heat capacity, through some algebra, we can use the PVT relationship to obtain a function that we can integrate to get the real fluid heat capacity. A similar analysis can be done for the C sub V. For this, we have to start from du and do a similar analysis. Now, maybe it's better that we take this one step further. Here we are going to evaluate this differentiation. This is going to be Cp minus Cp star. All right. The term in the integral is going to be del V over del T at constant P. Del T over del T, which is 1. So what we are left with is this term minus del V over del T at constant P. These two terms will cancel one another. So the second differentiation is going to give us T del square V over del T square at constant P dP. Now these two terms will cancel one another, all right? In the integral form, we can just keep that. Or we can revert back to the differential form, del Cp over del P at constant T is equal to minus T del square V over del T square at constant P. Now let's see, now we have our equation of state, cubic equation of state. For the sake of discussions and for the sake of its simplicity, I prefer to discuss this matter with Van der Waals equation of state, but there are more equations than Van der Waals equation of state. I strongly encourage you to check out your textbooks. I will refer to you to your textbook to equations of state such as Peng and Robinson, such as virial equation of state, such as Redlich-Wong, and so on and so forth. But I will use Van der Waals equation of state for its simplicity and because we extracted it by removing the assumptions from the real ideal gas equation of state. Now we have our equation of state. Here, this portion of the departure function is going to come from the equation of state, that. And this is going to come from the heat capacity information that we are going to measure how much heat do we need to exchange under constant pressure or under constant volume conditions. All right, we will measure this. Now then, if I know the heat capacity information, and if I know the equation of state, I should be able to obtain all of the thermodynamic variables, right? So that's the whole idea of the excursion that we are going through these real fluid property estimations. Now, let me just elaborate on this Van der Waals equation of state a little bit more to see how it behaves on a PVT diagram. So here, we have intensive volume, here we have pressure, and we are going to plot this on the liquid vapor transition domain. All right, we are going to plot the van der Waals equation of state in the liquid vapor transition domain. So let's remember how the liquid vapor transition domain looked like. Here we have liquid plus vapor. This point is our critical point. All right? It is specific to the fluid of interest. All right? This is the saturated liquid line. This is the saturated vapor line. Now, when I have a cubic equation of state, such as this, it is going to give me the isotherm in the following form. It is going to cross, but this is going to go through a minimum, another maximum, and it is going to cross to the other side. So this is a constant temperature line. On the liquid domain, the change in pressure does not induce too much change in volume. On the very large volumes, and consider this scale to be logarithmic, on the very large volumes, we have a constant temperature line that is very similar to the ideal gas law. P is equal to RT over V. But we have a strange behavior in between. We are going to evaluate we are going to determine the equilibrium pressure corresponding to this temperature, and we are going to derive the equations here, and we are going to find the van der Waals equation of state constants as a function of the critical parameters. Now, there is one aspect of this curve which is attributed to James Clerk Maxwell. It is the Maxwell's equal area construction. According to equal area construction, we can draw a horizontal line. Of course, my representation is a little bit it needs a little bit of polishing. Okay, so let me polish it like this. All right. That the equilibrium pressure corresponding to this temperature is going to be the pressure that is going to give me equal areas above and below. When I plot pressure as a function of volume, keeping the temperature constant. All right? So this is going to be my equilibrium pressure. This is one thing. Now, the other thing that we will learn about this cubic equation of state is that we have metastable states. All right? Between this is my stable equilibrium, right? This is my equilibrium pressure, and this is my stable equilibrium. But experiments show, and this equation also show, that it is possible to go below that equilibrium, remain in the liquid side, while keeping pressure low. So here, this domain is called the metastable liquid. And this domain is called the metastable vapor. Let's come to the critical temperature. Those isotherms will run like this. This is going to be a higher temperature, but at the critical point, this isotherm, the critical isotherm, is going to have a saddle point. All right, here we are going to have a saddle point. At the saddle point, we are going to have the first derivative of pressure, with respect to volume at constant temperature is going to be 0 because we're going to have an extremum, but also the second derivative. Given this, now let's take the van der Waals equation of state and evaluate these derivatives. The first derivative, del P over del V at constant T. Is equal to minus RT over V minus B square plus 2A over V cube. The second function, I'm going to take the differential a second time. This is going to be 0 at T is equal to T critical. When temperature is the critical temperature, pressure is the critical pressure, and volume is the critical volume. The second, del square P over del V square at constant T is going to be RT 2 over V minus B cube minus 6A over V to the power 4. This is also 0. Again at T is equal to T critical. And of course, P critical is going to be RT critical over V critical minus B minus A over V critical square also. All right? Now here, principle of extremum gives us two equations. We also have one equation. We can combine any two to obtain A and B as a function of critical constants. Now when we use these equations to evaluate A and B, we have A as a function of the critical volume, critical temperature of the fluid, and the universal gas constant. This is 9 over 8, and B as the critical volume divided by 3. And also we related the critical pressure to A and B, and now we have a new term called a Z critical. Z is the compressibility factor at the critical point, and it is the ratio of P critical, V critical over RT critical. Now if the fluid is an ideal gas, the compressibility factor is 1. Now the value of the compressibility factor or deviation from 1 tells us how far we are away from this ideal behavior. Now let us take this Z critical, P critical, V critical over RT critical and substitute these values. Let's see what we are going to get. P critical is A over 27B squared. So 1 over 27 of A, which is 9 over 8, V critical times RT critical divided by B squared. Divided by V critical square multiplied by 9. Now this 9 and 9 and 27 cancel to have 3. We have V critical cancelling with this one, RT critical over V critical, Z critical is equal to P critical times V critical over RT critical. We end up getting Z critical as 3 over 8. So this 3 over 8 is universal. If we have a van der Waals fluid, its critical compressibility factor is going to be 3 over 8. Well, we have a lot of fluids, especially organic fluids, who have close to 3 over 8 critical compressibility factor. But of course, we have many other fluids that deviate from that critical compressibility factor. But when van der Waals observed that there is a universal critical compressibility factor as such, he came up with the theory of principle of corresponding states. What he did was conceptualizing the fluid behavior relative to the critical point. So he came up with the reduced parameters. So we have T reduced, the actual measured temperature relative to the critical point, how far away from the critical point. Reduced pressure is P over P critical, and reduced volume as V over V critical. Now, given this, if we evaluate the departure functions relative to the reduced parameters, we have a universal diagram that we can use regardless of the fluid, and principle of corresponding state diagrams are available in the textbooks and also on the internet. So when we take this principle of corresponding states diagrams, universal diagrams, given that our compressibility factor follows the common denominator, that our fluid behaves similar to the critical compressibility factor that this corresponding states diagram has been derived, we can have a shortcut to evaluation of the enthalpies and internal energies of the real fluid.